All right, so now here we're going to talk about how we can incorporate entropy into second law of thermodynamics. So we talked about entropy from the macroscopic and microscopic probability point of view. Then one of the things we're going to start talking about here is in terms of indicate how to evaluate entropy numerically. That means how we can calculate entropy and discuss entropy for a macroscopic system with a huge number of particles. All right, so we already looked at the equation for entropy to be S equals KB, which is the Boltzmann constant, then ln of W. By the way, this W here is not the work done, right? So this W here has a completely different meaning. It represents the number of possible macrostates. That means, the W for the work done should not be confused with this W. That means W is pretty much represents probability. So the probability um, for the given microstate to exist. The units of entropy is same as units of the Boltzmann constant, which is um, joules per Kelvin. So how many joules per Kelvin, right? That's quantity that represented by entropy. Remember, entropy is a state variable. So we want to relate that to other state variables. Let's talk about, one, simple, scenario. One of the things we know about um, from kinetic theory of gases that you have the gas molecules that are moving around in some kind of container. So let's take some kind of container and talk about, we have molecules kind of moving around in this container. V representing the volume of the container. So they're pretty much confined, isolated inside the container. Now, in terms of for a uniform distribution of gas in the volume, there are a large number of microstates, which means that the position, for example, of those particles, you know, has a high probability into, like, let's say, has a very high uncertainty. It can be anywhere, right? So, for example, if you're considering this particle, at any given time, technically it can be anywhere inside this volume. Okay. So then what we can do here is we can look at the number of microstates, but considering the variety of molecular locations that available to molecules. Okay. Now, what we're going to do, I'm going to present Vm as the volume um, occupied by some molecule. So it has, basically each molecule now occupies some microscopic volume, Vm. So then the total number of possible locations for a single molecule in the microscopic volume V, this is going to be a ratio. So W is equals to volume divided by the volume of the molecule. Okay. Where this W here, lowercase w, basically represents the number of ways a single molecule can be placed in the volume or number of microstates for a single molecule. That means we're looking at in terms of remember every macroscopic, let's say you can have many microscopic, so let's say probabilities. So we have number of microstates for each macrostate. And in this case, this W represent basically the number of ways a single molecule can be placed. Okay. Now, we always assume that all the, let's say available locations, right? They have basically the probability for them are pretty much equal. That means it has equal probability to be, any of these locations. Okay. Now we can also assume that in terms of if we start adding more molecules, the number of possible ways that molecule can be positioned in the volume multiplies. Okay, so as we talked about previously in terms of having a one molecule on the left side and then two molecules on the left side, That means, for example, if I bring another molecule, then it's going to be W times W, or W squared. That means if I'm talking about then, probability of that, so it will be W times W, W squared, which means it will be V over Vm squared. Okay, where again, the uppercase W represents the number of ways of putting multiple molecules into a volume, and is not to be confused again with the work. So the work is, also capital, uppercase W, but this is not that. Okay, it's again, it's basically the probability of having number of, let's say given microstate, probably for the microstate to exist. Okay. Now, in terms of like, let's say you can see, right? So technically, two represents the number of, let's say, particles we have. In this case, number of molecules we have. So if we have n number of molecules, then the W will be equals 10 to basically W, lowercase w, right, to the n, which will be then V, the total volume over the microscopic volume to the power of n. So basically, we end up with this, okay, considering that we have n number of molecules in our container. Now, if I come back then and apply this to this original equation, then what we'll get here is entropy will be equals to Boltzmann constant times ln of, total volume over the the volume of a molecule to the power of n. And we always can, take down the n. So it becomes n kb ln of V over Vm. Now, if you remember, number of molecules times Boltzmann constant is equivalent to number of moles times the gas constant. That means I can also then rewrite this as nr times then ln of V over Vm. That means I can also write it like this. So, and what we can do here is you can use this expression later on to investigate the change in entropy, okay? Because we're already looking at that, the equation that we have here can be related to the thermodynamics, systems, okay? And this equation generally represents the spatial part of the entropy of the gas. That means, in terms of like, let's say space, right? So we have volume, how the volume, each molecule related to the total volume of the system, of the container, okay? That means that's why it's known as a spatial, let's say, portion or the property of the entropy of the gas. Okay, but what we have here is, for example, if you have a system where the volume doesn't change, right? Since let's say we're saying that the entropy related to this particular spatial property of the system. So if we're not changing the volume, does it mean that entropy is not changing? Well, there is a change in entropy. Entropy is changing, okay? Entropy is changing, but it's not really obvious by just looking at this equation. That means we can look at other ways to relate entropy to other, um, let's say the state variables, where we can see that change in entropy in terms of, let's say, for example, in terms of change in temperature, in terms of heat. Remember, heat is not a state variable, but remember, heat basically added or removed from the system directly related to the change in temperature. So now, one thing we can do here is then we can talk about in terms of how to, let's say, if we have a, let's say, temperature change in the gas, how that can relate it to the change in entropy. Because one of the things we have here is temperature is a state variable. That means it is independent of the path. When you go from one state to another, it doesn't really matter how we get from one state to another. What matters here is those two endpoints. Same thing then is true also for the entropy. That means we talk about pressure, volume, temperature, and internal energy. Those are state variables. Now, the new state variable here is also the entropy. So when you have changing, let's say you have two states, state one to state two, how you go from state one to state two, for this particular variables, it doesn't matter. They're path independent. So that's why we would like to relate entropy to other quantities as well. Okay. So now one of the things we can relate here is in terms of how if relate the entropy to the change in heat and temperature. Now, one thing we know about uh, the study of earlier parts of the chapter here is that if warm object is placed in thermal contact with cool object, the energy transfer from warm object to cool one by heat. Okay, which means there's energy transfer going from hot to cold. Okay, representing spread of internal energy until distributed more evenly between the objects. Okay, now what we're going to do is we're going to consider mathematical representation of this spreading of energy, equivalently change in entropy. Because if energy is spreading, there's a change in temperature. Well, if there's a change in temperature, we're going to see that there's equivalently change in entropy. All right. So one of the things we have is that the original formulation of entropy in thermodynamics involves transfer of energy by heat during a reversible process. Remember, reversible process is a highly theoretical process that assumes that there are no dissipative, forces, that energy is conserved, and assumes that basically the path, let's say is cyclic. So you go around and come back. And what we have here is the entropy being a state variable. So when you look at change in entropy during this process, again, it depends only, as I mentioned, right, on endpoints. And that's very important because sometimes when you have some kind of complicated process, you can change the type of calculation that you're doing based on the fact that entropy doesn't really matter which type of process you're using to calculate change in entropy. You can always choose the one that is simplest, because it doesn't matter how you calculate the change in entropy, what type of path you choose, you're going to get the same answer. Okay. So entropy change for irreversible process can be determined by calculating entropy change for reversible process that connects the same initial and final states. Which means that even though there is no such thing as reversible processes, all the real processes are irreversible, we can still use reversible processes to do calculation for example, for entropy. Why? Because the end result is exactly the same, regardless what type of, let's say, path we're taking. All right. Remember, one of the things we have about reversible and irreversible was that reversible processes were path independent, irreversible were not. So here we can then talk about that. That means the entropy change for irreversible process can be determined basically calculating entropy change for reversible processes. Okay, let's look at in terms of the type of calculation we can do. So change in entropy can be then represented as derivative of dq, right? Basically changing energy, changing heat divided by the temperature, and the temperature here has to be in Kelvin. So ds equals to dq over t. Now, one of the things I should mention here is that entropy is a state variable, temperature is a state variable, but heat is not. That means how you change, how you go from path one to, let's say state one to state two, doesn't matter for entropy, it doesn't matter for temperature, but it matters for heat. So sometimes you might see that this technically might be written in terms of, a derivative like that, kind of like a squiggly D. That's because, for example, if you're talking about ds, that's a, you know, you're talking about differentiating the state variable. Also, for example, dv, that's a differentiating a state variable. And one of the things we have for them, they are path independent. That means another way you can represent this type of differentiation here is as exact differentiation, because exact differentiations, they are path independent. Okay, that means whenever you integrating, they're independent of the path. So if I integrate dV going from V1 to V2, this is nothing but V2 minus V1. Okay. Now, in terms of then heat and work done, those are path dependent variables. Okay. So that's why for to use differential, different differential, right, to describe those, sometimes we do use this, so like a delta, right, squiggly, let's say D. So these are known. So let's say we have dq, or you can have this one as dw. Those are known as inexact differentials. Okay, because if we integrate over it, we must specify a path for that integral. Okay, where state variables, basically the state variables, they are using ds and dv, and those are basically exact differentials. That means we don't care about the path taken. Okay, so there's just a little bit of information about that, because sometimes you might see in some of the textbooks this guy here is given as like this. This means that's an inexact differential. That means that quantity is path dependent. Okay, now let's look at then in terms of this entropy equation, right? So we have entropy equation that is basically given in terms of dq divided by t. Okay, that means this is the mathematical representation of spreading of energy. Okay, or spreading of energy basically can also be represented as change in entropy. Okay, now dq is the amount of energy transferred by heat when system pretty much flows from one equilibrium state to another. Okay, remember, we're talking about reversible processes, but that means we're using reversible process to do our calculations. And remember, reversible process assumes that everything is done, so like so slowly that your system is always in equilibrium. That's why dq here, you can think like amount of energy transferred by heat when the system follows a reversible path. That means when you have from one state to another, you're talking about, a reversible process. So then the change in entropy basically equal to, dq, right? The amount of energy divided by the absolute temperature of the system. Okay. Now, in terms of then what we have over here, you can see that even the units follow the unit that we just talked about energy, the entropy using the other equation. It's joules per Kelvin. Okay, that means this is in terms of change in entropy for an infinitesimal process. And you can see, right, we're already dealing with, state variables. So these are thermodynamic process. Okay. Now, in terms of then relating this to the other equation, so the entropy is equals to Boltzmann constant times ln of W, where again, W is the numbers of microstates. So then from here, we can say that delta S, that means if I integrate both sides, so if I integrate both sides of the equation, left side of the equation, remember it's an exact differential. Okay, that means what I get here is just a delta S. Okay. On the right side, then what I have here is, inexact differential technically. So integral of the, dqr d, over t. So again, from initial to final. And then what we end up here is the equation basically equals to delta S times kb ln of then W final over W initial, where you can see, right, those W final initial are initial and final numbers of microstates for the initial and final configurations of the system. Okay, that means the number of microstates for the state one compared to the number of microstates for the state two, or initial state and final state. Okay. Now, if W final is greater than W initial, then final state more probable than initial state. So there's more choices of microstates, which always would mean that entropy would increase. Okay. That means whenever you go from state one to state two, if the W is greater than, that means the number of microstates higher for the state two compared to the state one, then your entropy basically will increase. Now, one of the things we can see here is um, we can talk about, let's say, what happens, right? What are the conditions? Can we have, for example, entropy that decreases if we do some kind of thermodynamic process? Those are some of the things we will be able to see. Okay, now, change in entropy of a system going from one state to another, again, has same value for all paths connecting the two states. What does it mean? It means that if I have a PV diagram, this is my state one, this is my state two, for example. If I look at then entropy at state one, then entropy at state two, and I look at change in entropy, this is going to be the same value if I go from one to two, taking maybe isovolumetric, then isobaric, or if I take isothermal, or if I take isobaric, then isovolumetric, or some random path, doesn't matter. Change in entropy is exactly the same. So finite change in entropy delta S of the system depends only on the properties of initial and final equilibrium states. That means it doesn't depend on the path. What it depends on is basically my state variable values of state one, V1, P1, T1, and state variables, basically also in internal energy at one, then V2, P2, T2, then internal energy 2. Okay, that means it only depends on this. That means you are free to choose any convenient reversible path or which to evaluate entropy. Okay, you can take something like this. You can take something like that. You can take something like this. No, for example, a lot of times isothermal process is probably the easiest one to use, and something that we can use also to do some calculations. All right. Here's in terms of we're going to consider a change in entropy that occur in Carnot heat engine that operates between Tc and Th. Now, one of the things we know about Carnot engine, remember it's a reversible engine, it's the theoretical reversible engine, and it's a cyclic engine, right? So basically you go from initial state and you basically go and doesn't matter what type of process you do, right? Come back. Remember, the Carnot engine specifically was in terms of the two isothermal and two adiabatic, compression and expansions. Now, here again, what we're going to do, we're going to consider in one cycle. What we can have here is in terms of how the entropy will change. So here's we start with this equation, change in entropy. So we're going to consider again Carnot heat engine, and we're looking at change in entropy. So change in entropy equals integral of dq over t. Okay. That means we're going to take energy to be QH from the hot reservoir, and QC going to be then energy that's going to be expelled to the cold reservoir. Okay. Remember, energy transfers occur only during reversible isothermal portion of the Carnot cycle. Remember, so if I draw the Carnot cycle PV diagram, so remember, so here's you have A, B, so you have and one isotherm like that. Let's actually write, draw the isotherms different colors. Okay. So what we have here is during one of the processes, that's an isothermal process. So during this process, you have then QH entering the system. Okay. Then you have an adiabatic process going from B to C. Remember, adiabatic means that no heat added or removed. And then you have a isothermal compression. And then you have adiabatic compression. Okay. Again, in this process over here, then you have a QC that is basically removed. That means energy transfers occur only during those, irreversible isothermal portions of the Carnot cycle. Okay. Then constant temperature. That means, if I'm considering those portions, right? Those portions of the cycle, it means temperature is constant. I can take it out of the integral. Okay, that means one thing I can do here is, uh, so if I remove the, the in terms of, like, let's say the temperature out of the integral, so the integral has a value of total amount of energy transferred by heat. That means equals to 1 over t, an integral of dqr going from initial to final state. Okay. Now, during the two adiabatic processes, Q equals 0, so the entropy changes are 0. That means for the process B to C, and we put it here D, then D to A. Remember, these are adiabatic. So for the adiabatic processes, Q was equals to 0, which means entropy change are 0, okay, for those processes. Okay. All right, so these processes, remember, is reversible. Then we can look at it in terms of um, over here, right? Kind of like integrating. So then this one will give us delta S is equals to, so it's going to give us QH over TH minus QC over TC. Again, put in absolute value. Now, what I have here is then, since what I have is the QC over QH, remember this ratio is equals to TC over TH. Then we can say that delta S equals, for example, then QH over TH minus, so here if I write QC is equals to, for example, QH TC over TH, then I can replace QC over here. So then becomes that's become QH times TC over TH divided by TC. So then TC over TC will cancel. Then I'm going to have then QH over TH minus, the only thing that survives here, then QH over TH, and that gives me 0. Okay. That means what we get here is during the adiabatic processes, the change in entropy were already 0. During that isothermal processes, then we calculate also to be 0. That means total entropy is 0 for the Carnot engine. Then you can pretty much think of it like this. So then total entropy, total change in entropy for Carnot engine operating in a cycle, right, is 0. That means you can say that it is 0 for any reversible cycle. Okay. So because entropy is a state variable and depends only on the properties of the given equilibrium state, that means we can assume that for this particular case, delta S is equals to 0, change in entropy, delta S, right, is equals to 0 for any reversible cycle. All right. So, go. Now let's look at in terms of, we're going to consider adiabatic free expansion of gas occupying initial volume VI, like given in the figure over here. And what we can assume that there's, remember we talked about this, there's a membrane separating the volume, initial volume that we have for the, occupied by the gas. And then we have then the vacuum on the other side, and the membrane basically separates them. So membrane going to be, broken. So if you break the membrane, then the gas will spread into the vacuum. Okay. Now, one of the things we have here is, remember we talked about, right? They don't do any work. So there's no work done. And what we have is that once you break the membrane, this process is irreversible. You can never assume that once the gas is spread into vacuum, then suddenly they can at any time come back and just basically accumulate in just original volume on their own spontaneously. Okay. The gas will never spontaneously crowd into half volume after filling the entire volume. Okay. Now the question is, what is the change in entropy of gas during this process? Now the question here is, um, how do we calculate change in entropy? So this process is neither reversible nor quasi-static. That means, as we said, right? So this process is irreversible. So if I want to calculate change in entropy, then what I need to do here is I need to find a way to relate entropy, right? Change in entropy to the other, let's say microscopic quantities. So for example, we need to find, you know, not only microscopic quantities, but also in terms of what is the amount of energy, right, transfer. So we need to find QR. So equivalent reversible path will give us basically same value, because at this point I have some kind of process and it's an irreversible process, but still initial and final states are same regardless of what type of process I would consider. And then one of the things I can do here at this point, I can choose any type of process I want to relate my initial and final states, and basically the entropy of initial and final states, so then I can find the change in entropy. And one of the easiest one, in my opinion, is isothermal process. Why? Because if I'm looking at the isothermal process, then this equation for entropy, delta S, which is the integral of dq over T, well, in this case, for isothermal process, temperature is constant. So it just becomes integral of dq. Okay, integral of dq. Also for the isothermal process, well, there is no change in temperature, right? And there is no change in internal energy, which means that in terms of, let's say, Q, sorry, let's say change in temperature is zero, which means change in internal energy is zero, and change in internal energy, remember, was Q minus W. So then what I can do here is I can relate those. So I can say that this is the amount of energy that I'm considering, right? So, and what I have here is, since the internal energy is zero, that means Q is equals to W, or by the gas, or negative of W, which is the work done on the gas. Okay. That means this integral of dqr going from initial to final states is equal to the work done by the gas or negative work done on the gas. Okay. So then what I can do here is, remember then that work done for the isothermal process is equals to nr ln v final over v initial. Okay, which we looked at earlier, right? That means one of the things I can do here is I can say that in terms of my change in entropy, then is equals to nr then ln of v final over v initial. Okay. So, all right. So remember, so again, write down work done is equals to nRT ln v final over v initial. That was the work done. That means when I replace this with 1 over T nRT ln of the ratio v final over v initial, the T cancels out, and change in entropy basically ends up with this. Okay. Now, one thing we have is that because, let's say, for example, v final is greater than v initial, then we consider then delta S to be positive. Okay. So this positive result indicates that the entropy of the gas increases as a result of irreversible adiabatic expansion. Okay. All right. So the entropy of gas increases as a result of irreversible adiabatic expansion. Now we can look at in terms of entropy change in thermal conduction. So we consider a system consisting of hot reservoir and cold reservoir in thermal contact and isolated. Then we can say that change in entropy of a system is delta S equals Q over Tc plus negative Q over Th. So equals Q over 1 over Tc minus 1 over Th. And it's going to be greater than 0, which is consistent with the interpretation of entropy changes representing spreading of energy. In initial configuration, hot reservoir has excess internal energy relative to cold reservoir. The process spreads energy into more equitable distribution between the two reservoirs. Okay. So the total entropy always increases when heat flows from a warmer object to a colder one in an isolated two-body system. That means the previous slide basically had an isolated two-body system with the different temperatures, and energy always goes from hot to cold, and the total entropy always increases for this type of process. So the heat transferred is the same, and the cooler object is at the lower average temperature than the warmer one. So that entropy gained by the cooler one is always more than the entropy lost by the warmer one. Now, another thing we can do here, let's finally look at some examples where you can see how we can calculate entropy. Let's say we have a solid that has a latent heat of fusion, LF, melt at the temperature Tm. So we're going to calculate the change in entropy of the substance when a mass m of the substance melts. Okay. So what we're given here is we want to find the change in entropy. So then change in entropy is equals to integral of dq over t. All right. So one thing we have here is that we know that during the melting process or freezing process, right, the temperature remains constant. That means any solid, when it's melting, let's say it's ice cube, right? For example, ice cube first has to reach temperature of 0 degrees Celsius. Then during the entire melting process, it remains at 0 degrees Celsius. That means the temperature is the same. So in this case, that means I can remove the temperature, T melting. So technically, I don't know if it's an ice cube or not. So I'm just going to write whatever solid object this is. It's 1 over the temperature, its melting temperature. Then integral of then dqr. All right, so then integral of dqr. So basically, it's going to be then qr over tm. And this is the latent heat. So mass, delta m times LF, then divided by Tm. Okay. That means what we have here is, you can say then that's basically the equation that we have, or we can just write in terms of LF times M divided by Tm. Okay. Now, because again, the melting takes place at fixed temperature, we can think of this as an isothermal process. Okay. So then we can use equation. So this is basically that isothermal process equation. Okay. Now, the Dm is positive. LF is a positive quantity. That means entropy is positive, or change in entropy is positive. That means representing that energy is added to the substance. Okay, so since it's melting, right, so the energy has to be added to the system. Okay, so that entropy basically is positive, means, or change in entropy is positive, means entropy has been increased. Here's another example. 150 gram insulated aluminum cup at 15 degrees Celsius is filled with 250 grams of water at 100 degrees Celsius. We want to determine the final temperature of the mixture. So determine the total change in entropy as a result of the mixing process. So we're going to use delta S is equals to integral of dq over t. Okay. Now, what we have over here is we're given the mass of the cup, 150 gram at initial temperature of 15 degrees Celsius. And then we're given the mass of water, 215 gram, and its initial temperature at 100 degrees Celsius. Okay. That means what we have here is that the equilibrium temperature for both of them will be the same, right? I mean, you have two objects at a different, temperatures put together, then there will be heat exchange between them until the mixture eventually has the final temperature. Now, one thing we know that is Q water plus Q aluminum, let's say, going to be equals to 0. And since none of the have undergoing any type of phase change, we can write them as mass of water, specific heat of water, times T final minus T initial, then plus mass of aluminum times specific heat of aluminum, times T final minus T initial. Then what we know here is the T initial of water is equals to 100 degrees Celsius. T initial of aluminum is equals to 15 degrees Celsius. And we can always replace those things. Now, our goal here is to basically find the final temperature. Okay, that means we just write this as mass of water, specific of water, times T final, minus mass of water, specific of water, times T initial, then plus mass of aluminum times specific of aluminum times T final, minus mass of aluminum times specific of aluminum times T initial. And that's equals to 0. Now, we just then keep the terms that have T final and move the other terms that have T initial to the other side. That means mass of water, specific of water, T final, plus mass of aluminum, specific of aluminum, T final, equals to then mass of water, specific of water, T initial, plus mass of aluminum times specific of aluminum, T initial. Okay. Then here we factor out T final. Right, so if we factor out T final, then we can divide both sides by the sum of the mass of water plus specific of water plus mass of aluminum times specific of aluminum. That means divide both sides by this. Okay. And then we can calculate basically the final temperature. So let's cancel out. That's basically T final. All right. So imagine, right? So basically we just plug in all the values and calculate it. So if I have then T final equals to, all right, so the mass of water here is 0.215 kilogram times specific of water, which is 4186, times initial temperature, which was 15 degrees Celsius, sorry, 100 degrees Celsius, then plus mass of aluminum, 0.15, times 900 joules per kilogram for the specific heat of aluminum, time initial temperature of 15 degrees Celsius, then divided by 0.215 times, so 0.215 times 4186, which is the product of mass and specific heat for water, plus the product of mass and specific heat of the aluminum, which is 0.15 times 900. Okay. Plug in everything, calculate, we get 89 degrees Celsius. So that's basically in terms of the final temperature. Okay. Now that we have that, we can then calculate change in entropy. Okay. Because one thing we have here is change in entropy. Let's then kind of give myself a little more room over here at the top. All right. So Let's make a different color so we can separate them. All right, so if we calculate change in entropy, so this will be change in entropy of the aluminum cup plus change in entropy of the water. So this means integral going from T initial of aluminum to T final of aluminum. Then you have dq over T. So this is for the aluminum. So then plus integral of T water initial to T water final. Then dq water over T. So this is equals to, then what I can do here is I can assume that when I'm looking at dq, so this is mc delta T, but since I'm looking at the differential of the Q, this becomes dt. So where m times m and c, m times specific heat, those are constants. So m aluminum, specific of aluminum, then integral from T aluminum initial to T aluminum final, then dt over T, then plus mass of water, specific of water, then integral of T water initial, T water final, then dt over T. Okay. Which means then what I'm going to get here is aluminum, specific of aluminum, then this integral, those integrals going to give me nothing but, so it's dt over T, so that means 1 over T dt integral, so it's going to give me an ln over T final over T initial for aluminum, plus mass of water, specific of water, then ln of T final over T initial for the water. That means taking all the temperatures. So for example, temperature initial for water is 100 degrees Celsius. But remember, so we're talking about T, not dt in those equations for the entropy, change in entropy. So T initial is 100 plus 273. So it's 373. Then T final for the water will be 89 plus 273. Same thing for the initial temperature for the aluminum. So this will be 273 plus 15. That means you have to make sure that all the temperatures over there in Kelvin rather than in degrees Celsius. So if we do all the calculation, plug in the values, what we'll get here is 3.7 joules per Kelvin. Plug in everything, and that's a change in entropy. So entropy is change in entropy is positive, entropy is increased. All right, so next we're going to look at adiabatic free expansion. So we're going to revisit it, and we're going to look at it in terms of how we can represent that adiabatic free expansion in terms of macroscopic and microscopic approach. So let's verify that macroscopic and microscopic approach to the calculation of entropy lead to the same conclusion for the adiabatic free expansion of the ideal gas. Suppose the ideal gas in the figure expands to 4 times its initial volume. That means we have VI, and then V final is equals to 4 times VI. Okay. As we have seen for this process, the initial and final temperatures are the same. Okay. Using a macroscopic approach, calculate the entropy change for the gas. Then, using statistical consideration, calculate change in entropy for the gas and show that it agrees with the answer you obtain in part A. All right. So in terms of then for part A, okay, so what I can do here is using the macroscopic approach, that's change in entropy equals NR, then ln of V final over V initial. So then this can be then NR ln of, well, V final is 4 times V initial divided by V initial. This will cancel out. So we get NR ln of 4. So that's the answer for part A. That means our calculation for change in entropy is equals to nr times ln of 4. Now, next, we're going to look at in terms of the statistical consideration. That means using the value of delta S equals then KB ln of, ln of W, where just W here is the probability of the macrostate. So let's look at that approach. So what we have here is, then we can think of it like, let's say, the Wi being equals to, then this is your initial state, right? So then this is the, lowercase wi times to the power of n, as we discussed in earlier. So the lowercase basically represents the probability of a sort of like a single molecule, and you have then n number of molecules. So then we saw that this is equals to then v initial over vm, right? That means the initial total volume divided by the volume of the single molecule, then raised to the power of number of molecules that we have. Then W final is equals to, again, remember, these W's are not work done, right? Those are basically the statistical, probability representation of the, macroscopic, let's say, state. So this is then, similar way we can do in terms of V final over Vm, but now we know that V final is 4 times Vi over Vm, and these are to the power of n. Okay. Then change in entropy is equals to Kb, then ln of W final over W initial, which is equals to Kb ln. Then what we have here is, so I have W final is 4V initial over Vm divided by Vi over Vm. In a way, I can raise those to the power of n. So like that, right? So then this is, you can see the Vm is going to cancel out. So then what you have is that Kb ln of 4Vi over Vi raised to the power of n, or change in entropy is equals to Kb ln of 4n. So which then will give you, so I can basically put that n in front of it, so it becomes n Kb ln of 4, and nkb, remember, is equivalent to nr. So nr ln of 4. And that answer agrees with the answer in part A. Okay. So next, let's say what we want to do here is, if for this type of process, I could come to the same final answer if, let's say, we didn't use another equation. Remember, the way we derived this equation when we first talked about this process, that means adiabatic free expansion, I said that this is basically a irreversible process, but I can use a reversible process to calculate change in entropy, because entropy is a state variable, and the state variables can be calculated either by reversible or irreversible equations, and there's going to be the same thing. It's easier to use the reversible process, because using the reversible process we could easily calculate then change in entropy. Now what I can do here is I can show that I can get the same thing even if I choose a different path. That means, for example, let's use so let's say if I have a PV diagram like this, right? So for example, state 1, state 2. Remember, we have an adiabatic free expansion. What it means is that adiabatic means that you have um, this is being, let's say, one isotherm, this is being another isotherm. So you go from state 1 to state 2, such that you go from one state to another where you have basically a change in temperature. Remember, the adiabatic always assume that there is a change in temperature, because remember, change in internal energy is equals to Q minus work done, but Q is equals to 0, but change in internal energy would change because there was, you know, let's say some kind of work done by the gas or on the gas. So that means what we can think about here is that this is adiabatic free expansion, right? So there's an adiabatic process. So I can technically get to that, for example, using a different path. Okay. So let's say that let's go back to the next page. Okay. So for that adiabatic, expansion process, right? Let's use a reversible isovolumetric process. Okay, it's going from B to C, right? We're going to be using that. That means I'm using delta S. Let's choose a little bit different color here. So delta S, change in entropy, is equals to integral of dq over t. So what I'm going to do here is I'm going to say that dq. Okay, remember, sometimes you can also write like this for dq because it's not a state variable, it's a path dependent. So what we're going to do, we're going to assume that we're dealing with the isovolumetric process, isovolumetric or isochoric, right? That means constant volume. And then in that case, dq going to be equals to n cv dt. So then if I have integral of n cv dt over t, and in this case, it will be between t2 and t1. Okay. So then this is equals to n cv can come out of the integral and just become integral of t2, t1. And here we have dt over t. Now, dt over t just going to give us ln of t with the limits of t1 over t2. So it's basically going to be t1 over t2. So ln of t1 over t2. All right. So from here, what we can do is this. Let's look at what the ratio of t1 and t2 is, because t1 and t2 is a temperature of state 1 compared to state 2. Then what we know here is this ratio will be also equals to V final over V initial gamma minus 1, because it's adiabatic expansion. So then this is equals to V final is 4V initial over V initial to the gamma minus 1. V initials cancel out. So then you have 4 to the gamma minus 1. Okay. That means if we go back to then our original equation, change in entropy is equals to NCV ln of 4 gamma minus 1. Okay. Now, what I can do, I can say NCV times gamma minus 1 times ln of 4. Okay. And if you remember, right, gamma is equals to the ratio of Cp over Cv. So I can say that then change in entropy is equals to NCV, then ratio of Cp over Cv minus 1 times ln of 4. Okay. Then from here, that will cancel out. And then what I have here is I have n times Cp minus Cv, right? If I distribute Cv, then times ln of 4. And if you remember, right, Cp minus Cv is nothing but the gas constant R. That means change in entropy is equals to nR ln of 4. Exactly same result as before. Next, we can talk about how then entropy changes depending on the type of uh, process we have. So you have a reversible process compared to irreversible process. What we have is this: the fact that after every interaction, the entropy of the system plus the environment increases is another way of putting the second law of thermodynamics. Because one of the things we have here is this: the entropy of an isolated system never decreases. It is either stays constant if the process is reversible, or increases if the process is irreversible. I showed you in an example how the change in entropy equals zero for the Carnot engine. That means it's a reversible process, and the change in entropy was equals to zero. And then I showed you that for the other examples, the change in entropy was positive. That means entropy was increases when you have a irreversible process. Now, what we can do here is we can say then change in entropy is equals to, so if you consider change in your system and entropy of your system plus change in entropy of the environment, this will be zero if you have a reversible process, or change in entropy is equals to change in entropy of the system plus change in entropy of environment, then going to be greater than zero always for irreversible process. So for irreversible process, okay, that means what we have is entropy or change in entropy can never be negative. Entropy either stays the same for the reversible processes, or it increases for the irreversible processes. That means when you're including change in entropy of your system and change in entropy of the environment combined together, you always get either constant or increase in entropy. So then what we can say here is then another way to put the interentropy is in terms of order to disorder. Entropy is a measure of the disorder of a system. So this can give us another way of looking at the second law of thermodynamics. Natural processes tend to move toward a state of disorder. And here's an example, right? If you put milk and sugar in your coffee and stir it, you end up with a coffee that is uniformly milky and sweet. No amount of stirring will get the milk and sugar to come back out solution. Or imagine if you have some kind of container with a layer of, for example, pepper and salt, and you have basically a layer of salt and then layer of pepper. Then if right now you have sort of like order, if you shake it, then they're going to mix. So then what you have here is that no amount of time can give you, let's say, the system basically go back to becoming layered sugar, salt and pepper. Okay, that means what we have here is your system will always go as entropy, right, is a measure of the disorder of the system, and natural processes tend to move toward state of greater disorder. Another thing we have here is some sometimes when you look at the process, especially the natural processes, some energy becomes unavailable to do useful work. Okay, that means, for example, when we have a heat engine, remember the energy flows from hot to cold. Okay, so as long as the temperature for the hot reservoir higher than the temperature of the cold or low reservoir, heat will flow from hot to cold, and then you can use some of that energy to do some useful work. But think like this: if you have, this is your hot reservoir, this is your cold reservoir, and then energy as it's flowing, then some of it goes into doing work. Well, this is TH and this is TC. Well, eventually think like this, right? Eventually, maybe the hot reservoir, as it keeps losing energy, will cool down, and cold reservoir, as it keeps gaining energy, will warm up. And closer their temperature to one another, less energy will be moving from one system to another. Eventually, then they will reach the same temperature. Then there will be no longer any type of heat available to do useful work. So that's why in any natural process, some energy becomes eventually unavailable to do useful work. Same thing you can think like, let's say when the object is falling, so then you have kinetic energy, which is, kind of like ordered energy. And then when it hits the ground, then some of that energy then can be, like, let's say in terms of disorder, right, becomes, let's say the thermal energy. But eventually, let's say the object will stop, it will hit the ground and it will stop. So then it no longer has energy that can be converted into some kind of useful work. Okay. That means if we look at the universe as a whole, it seems inevitable that as more and more energy is converted to unavailable forms, because once it goes to QC, right, basically this, the cold reservoir is no longer available, let's say. So once the energy is converted to unavailable forms, because for example, kinetic energy converted to heat energy, you cannot really convert it back to kinetic energy. So when the object falls down, hits the ground, that kinetic energy is converted to heat energy. And heat energy then, some of that energy goes into warming up the surface, heating up the, like air molecules, a little above the surface. But then you will never have that energy be useful to you due to some kind of, let's say mechanical work. Okay. That means the ability to do work anywhere will gradually vanish. This is called the heat death of the universe. All right. Now, in terms of third law of thermodynamics, as I mentioned, I will briefly, also talk about that. And what we have is that, remember the maximum efficiency of a heat engine. E is equals to 1 minus TL over TH. So what we have there is no way to achieve a temperature of absolute zero. Okay. So technically then the third law of thermodynamics basically give us that. It says it is not possible to reach absolute zero in any finite number of processes. Remember, so the idea here is if you have a finite number of processes, right, that means your TL will always be greater than zero, which means that only when this term is equals to zero due to the TL being equals to zero, then you can have 100% efficiency. And the third law of thermodynamics tells us that that's impossible. So it's not possible to reach absolute zero in any finite number of processes. So that means again, you can go and think of like some kind of theoretical where you can have infinite amount of processes, but you can think of like that. Quantum mechanics basically forbids that. So what we have here is then same with the third law of thermodynamics. It says that it's not possible to reach any absolute zero in any finite number of processes. Again, so we're not really doing anything with this. It's just interesting, let's say fact to know. And this is basically the third law of thermodynamics.